Every summer, as predictable as the tides, the UK railways seem to grind to a frustrating halt. It's a familiar story, a recurring inconvenience that leaves countless passengers stranded and schedules in disarray. As temperatures soar, often to levels that, frankly, aren't even that extreme compared to other parts of the world, social media fills with photos of crowded, sweltering platforms, a testament to the disruption and discomfort experienced by everyday commuters, and angry posts, train cancelled, no explanation, just weather. The digital cries of exasperation echo the real-world frustrations of those affected. It's chaos from London to Glasgow, a nationwide headache that disrupts travel plans and daily routines. People fanning themselves with newspapers and travel brochures, sharing water, offering what little relief they can to fellow sufferers, staring at boards flashing delayed and cancelled, the dreaded words that signal further uncertainty. It feels baffling, almost absurd. We're a modern country, a nation of innovation and engineering. How can a bit of sunshine cause this much trouble? It seems like a problem we should have solved by now. I spoke to Sarah, a commuter stranded in Manchester last July, a typical example of someone caught in the summer rail chaos. 3 trains cancelled, the station was packed, boiling, and no one told us anything. A common complaint highlighting the lack of communication and support during these disruptions. She's not alone. Thousands ask the same question year after year. Why does hot weather paralyze our trains? What is it about the heat that brings our railway system to its knees? It's not just passengers. Drivers, staff, and engineers, the people who keep the trains running, are on the front lines, battling the heat and its consequences. One network rail engineer told me, speaking anonymously about the pressures they face, "We know it's coming, but it's like fighting a fire on 100 fronts." A vivid description of the scale and intensity of the challenge. Teams work in scorching heat, checking miles of track, often in uncomfortable and demanding conditions, trying to prevent disaster, working tirelessly to ensure the safety of passengers and the integrity of the network. The public sees delays, cancellations, and overcrowded platforms, but not the round-the-clock effort to keep the railway from falling apart. The unseen work that goes on behind the scenes. This isn't just inconvenience, it's a massive operational challenge, a complex logistical puzzle that demands constant attention and resources. So what's really going on? What are the underlying factors that contribute to this annual disruption? Why does a few days of sun defeat our railways? Why can't we seem to adapt to relatively moderate heat? The answer is complex. Physics, the legacy of history, and the growing pressures of a changing climate all play a part, intertwining to create this recurring summer crisis. To understand, we need to look beyond angry tweets and social media complaints, and down to the tracks themselves, the very foundation of our railway network. What happens when steel meets a heat wave? What are the physical properties at play? The problem is real, puzzling, and affects millions, impacting lives and livelihoods across the country. Let's dig into the science and the potential solutions that could help us overcome this annual challenge. Why do our trains stop when the sun comes out? What are the specific mechanisms that cause this disruption? Let's find out. Let's unravel the mystery of the UK's summer rail woes. The heart of the problem, the reason why trains face disruption in the summer heat, is thermal expansion. It's a fundamental property of matter that has significant consequences for our infrastructure. When materials heat up, they expand. This is a basic principle of physics, affecting everything from bridges to buildings, and especially steel rails. For steel rails, this means they get longer in the sun. The intense solar radiation causes a noticeable increase in their length. On a hot day, rail surfaces can reach over 50 degrees Celsius, sometimes even higher depending on the intensity of the sun and the surrounding environment. That's much hotter than the air temperature that is reported in weather forecasts. The dark color of the steel absorbs heat, leading to this significant difference. Every molecule in the steel vibrates faster, gaining kinetic energy and pushing its neighbors away. This increased molecular motion is the driving force behind thermal expansion, ultimately making the rail expand. These expansion joints are designed to accommodate some of this growth, but they have their limits. A few millimeters per rail might not sound like much on its own. It seems insignificant at first glance, but over miles and miles of track, it adds up to a considerable amount of expansion. The cumulative effect is what causes the problems. Rails are held in place by sleepers, which are designed to maintain the correct gauge and provide support, and ballast, the stones that surround the tracks, providing stability and drainage. This entire system is designed for typical UK temperatures, taking into account the expected range of weather conditions. But with more frequent and intense extreme heat events, the infrastructure faces unprecedented challenges. The system is pushed to its limits, and sometimes beyond, leading to potential failures and disruptions. The expanding steel has nowhere to go, as it's constrained by the sleepers and ballast. As a result, immense pressure builds within the rails. This pressure can become so great that it overcomes the track's resistance. Imagine pushing both ends of a ruler towards each other. What happens? Eventually, it bends and buckles under the compressive force. That's precisely what happens to the rails when they experience excessive thermal expansion. They can buckle sideways, creating dangerous kinks and posing a significant risk to train operations. These buckles are a real threat to safety, potentially leading to derailments and other serious incidents. The system, in many places, was never originally built or designed to withstand this kind of sustained extreme heat. And as our summers get hotter and more prolonged due to climate change, the risk of these incidents grows exponentially. The underlying science is relatively simple to understand, but the consequences for our transportation network are huge and far-reaching. A few degrees difference in rail temperature can mean the difference between a smooth, on-time journey for passengers and a major disruption that leaves people stranded and inconvenienced. So, when the sun beats down with its full intensity on a hot summer day, the rails, absorbing that energy, start to fight back against the constraints placed upon them. And that's when the trouble really begins, leading to delays, cancellations, and potential safety hazards. Let's take a closer look at what happens when tracks bend and buckle out of shape under the extreme pressure of thermal expansion. Track buckling isn't a slow bend, it's sudden and dramatic. The compressed steel releases its force, pushing the track sideways, sometimes by feet. A straight line becomes a snake-like curve, a buckle. At high speeds, this is dangerous. A train could derail. That's why, during heat waves, the system goes on high alert. Engineers patrol the lines, measuring rail temperatures and watching for early warning signs. If they spot a sun kink, they act fast to prevent disaster. The first defense: speed restrictions. Slower trains put less stress on the rails. It's frustrating, but it's about safety. Sometimes, despite precautions, a track buckles and the line must close. Repairs are tough, often taking hours and causing major delays. That's why a bit of sunshine can strand thousands. It's not just the rails. The problems extend upwards too. The entire electrical system that powers these trains is susceptible to the heat. Overhead power lines, crucial for delivering electricity to the trains, suffer in the heat too. The high temperatures can have a significant impact on their performance and reliability. Electric trains rely on overhead wires, a continuous source of power that allows them to travel long distances without needing to refuel. These wires are kept at precise tension to ensure consistent contact with the train's pantograph, the device that collects electricity from the overhead lines. Like rails, these copper wires expand in the sun. Copper, being a highly conductive metal, is also very sensitive to temperature changes. As they heat up, the wires expand and start to sag, losing their original tension and potentially causing problems for the trains. If they sag too much, a train's pantograph can snag on the wire, creating a dangerous situation. This can lead to snapping the wire and shutting down the line, causing significant disruption to train services. This dewirement can halt entire sections of the railway network, leaving passengers stranded and causing widespread delays. The repairs can take hours or even days, depending on the extent of the damage and the location of the break. Modern systems use counterweights to keep wires taut, automatically adjusting the tension to compensate for temperature changes. However, many UK lines still use older equipment, making them more vulnerable to the effects of heat. On these routes, sagging is a real risk, a constant threat during periods of hot weather. To mitigate this risk, speed restrictions are often imposed. Slower trains reduce the chance of snagging a low wire, minimizing the potential for damage and disruption. Upgrading to auto-tensioning systems is underway, a long-term solution to the problem of sagging wires. But it's a slow process, requiring significant investment and careful planning. Until then, heat waves mean more delays, a frustrating reality for passengers and train operators alike. The delays stem not just from the rails, but from the sky above, highlighting the vulnerability of the entire railway infrastructure. The challenge is everywhere, on the ground and overhead, demanding a comprehensive approach to mitigation. keeping the power flowing is as tough as keeping the rails straight, requiring constant vigilance and maintenance. Both are vulnerable when the temperature rises, underscoring the need for innovative solutions to protect the railway from the impacts of climate change. So, what's being done? The most common response is speed restrictions. Slower trains mean less stress on rails and wires. It's not ideal, but it's effective. Safety comes first. Another tactic: painting rails white. Light colors reflect heat, keeping rails cooler by up to 10 degrees Celsius. This simple trick can prevent buckling in critical spots. Monitoring is key. Special trains packed with sensors scan the network for trouble. Data helps engineers target inspections and paint jobs before problems escalate. Long-term upgrades are happening. New rails are pre-stressed to handle more heat, and old wires are replaced with auto-tensioning systems. These changes take time and money, but they're making the network stronger. Technology and old-fashioned paintbrushes work together to keep trains running. It's a constant battle against the sun. Every summer, the playbook gets a little better, but the heat keeps raising the stakes. The race to adapt is on. Frustrated passengers often ask, how do Spain or Australia cope? Their railways are built for heat from the start, using heavier concrete sleepers and setting rails at higher neutral temperatures. In the UK, rails are set for 27 degrees Celsius. In hotter countries, it's 40 degrees Celsius or more. This gives them more leeway before buckling. White-painted rails and auto-tensioning wires are standard abroad. Real-time monitoring is widespread, allowing quick responses to heat risks. The difference? Their infrastructure was designed for heat. Ours was built for a milder climate. The UK's Victorian-era network can't be upgraded overnight. Retrofitting is slow and costly, but necessary. We're playing catch-up, adapting an old system to a new reality. Other countries had a head start. We're learning fast. The real issue is climate change. UK summers are getting hotter, and heat waves are more frequent. Our railways, built for a temperate climate, now face southern European conditions. The once-in-a-lifetime heat wave is becoming the new normal. This demands a fundamental rethink. Piecemeal fixes aren't enough. Experts call for major investment in climate resilience, upgrading tracks, power lines, and drainage. It's about future-proofing the entire network. This isn't just a UK problem. Railways worldwide are adapting to new extremes. From melting permafrost to rising seas, the challenges are global. Innovation is key. New materials, smarter monitoring, and AI-driven solutions. The question is, can we adapt fast enough? The pressure is on to keep the country moving. The future of rail depends on how we respond now. Making railways heat resilient isn't cheap. Billions are needed for upgrades. The cost falls on taxpayers or passengers, raising tough questions. But the price of inaction is higher. Every heatwave shutdown costs the economy millions. Reliable trains are vital for society. Missed appointments, lost business, and eroded public trust all add up. If people lose faith in trains, they'll drive more, increasing congestion and pollution. Investment in resilience is an insurance policy for the future. The debate isn't if we should act, but how and how fast. It needs government vision, industry commitment, and public support. Prioritizing projects and finding efficient solutions is essential. This is a national challenge demanding a coordinated effort. The goal: railways that can withstand the pressures of the 21st century. Despite the challenges, there's hope. UK engineers are pioneering new technology and smarter systems. Remote sensors now monitor rail temperatures and wire tension in real time. AI predicts trouble spots before they become disasters. Research into new materials and construction methods is underway. Stronger rails, better sleepers, and advanced overhead lines are being developed. These innovations won't arrive overnight, but progress is real. The goal: a railway that runs safely, whatever the weather. The journey is long, but we're on the right track. Lessons from recent heat waves are shaping a more resilient future.